Hello friends, we have covered part 1 and part 2 of unit number 5 flow through pipes, that is losses in pipes, major loss and minor loss, and siphon, pipes in series and pipes in parallel. Now let us move towards the last part, that is part number 3 of this unit number 5 flow through pipes. Part number 3 includes the dimensional analysis as well as the model analysis. Dimensional analysis is a very important tool for the problem analysis. First of all, let us see the objective of dimensional analysis. Now, as you know that all the real flow problems in fluid mechanics are solved by using equations, and some analytical procedures. But the solutions of these real problems depend totally on the experimental data, and the experimental data which is obtained is very huge. Means you, for obtaining the solution, you have to perform large number of experiments. Sometimes the experimental work in the laboratory is not only time consuming but also expensive. So to reduce the number of equations or to reduce the number of experiments, you are using dimensional analysis technique. So this dimensional analysis is an important tool which helps in correlating the analytical results with the experimental data, and this is very important as well as useful tool for the analysis of the data. So let us see how this analysis is performed. Now, as we have seen, in many cases the variables involved in physical phenomenon are known to us. Means in the given problem, the given variable, which is dependent variable, is a function of different independent variables. Okay, so number of variables are known, but the relation between these variables is not known. Such a relationship can be set by using dimensionless group of these variables, and these dimensionless groups are nothing but the non-dimensional numbers, which we can call as a dimensionless groups. Now the procedure for formation of these groups is known as dimensional analysis, and this procedure requires very less experimentation, and the nature of experimentation is considerably simplified. Means the numerical or the given problem, if it is including number of variables, then your number of variables are reduced to less number of variables using dimensional analysis techniques, because you are reducing that into non-dimensional numbers, combining the variables. Okay, so remember, the main objective of dimensional analysis is to reduce the number of variables for simplicity in obtaining the solution, as well as to reduce the number of experimentations. Now the things will be very clear from the following examples. Let us see one example for understanding this dimensional analysis. Consider a steady flow for an incompressible Newtonian fluid through a long, smooth-walled, horizontal circular pipe. Now, it is desired to measure the pressure drop per unit length of the pipe without the use of experimental data. Now, we have to form a correlation between this pressure drop and the variables of the pipe, like diameter, density, viscosity, and velocity. So the first step, you have to choose the number of variables, including dependent as well as independent variable. Now in this problem, it is given that the variables, independent variables, are diameter d, fluid density rho, fluid viscosity mu, and the velocity capital V. And the dependent variable is delta P, because we want to find the pressure. Okay, that is the pressure drop, delta P. So delta P is a dependent variable, and d, rho, mu, V are the independent variable, and we want to find the relation between these dependent variable and independent variables. Now at this point, the nature of function is unknown to us, and we have to perform the experiments to determine the nature of function, or we have to form the correlation. Now in order to in order to form the correlation, the experiments which should be performed should be in a systematic and meaningful manner. So it is necessary to change one variable at a time, keeping the others constant, and measure the corresponding pressure drop. Now if you see, if you perform the experiments, then the dependent variable delta p you have to measure for each of the independent variable. But to measure the independent variable, you have to vary the remaining independent variables, keeping the remaining independent variables constant. Suppose if you see in the figure A, you are varying delta p with V. Okay, there is a variation of pressure drop with velocity, but at that time you have to keep other three terms or the other three independent variables d, rho, mu as a constant. Similarly, delta p varying with d, delta p varying with rho, and delta p varying with mu. Okay. So all these experiments are performed keeping other variables constant. But the problem in this is that if you see the figure C and D, then delta P variation with density keeping D, V and mu constant is very difficult, because if you vary density, then the viscosity may also change. If you vary viscosity, then density is also going to change. So to vary one parameter keeping other parameter as a constant is a very difficult task in experimentation. So to reduce this number of experimentations, we are defining some non-dimensional numbers, or you can say dimensionless numbers. Okay, so what will happen if we reduce the number of variables? Now a simple approach to this problem is to collect two non-dimensional combinations of the variables, that is dimensionless groups. Okay, such that now in this there was delta p as a dependent variable and rho, v, d, mu all were independent variables. Now if you see, the combination has been made such that delta p into d upon rho v square has become one dimensionless number, and rho vd by mu has become another dimensionless number. So these two dimensionless numbers have been formed using the dimensional analysis technique, and the number of variables which were 5 initially, they have been reduced to only 2, and simply you can plot the graph of delta p versus the delta p into d into upon rho v square versus rho vd by mu. So you can see the graph in this figure number 2, that the one dimensionless number is on y-axis, and the other one, that is rho vd by mu, which is nothing but Reynolds number, it is on the x-axis. So it is easy to obtain the relation between the two dimensionless numbers, and it will give you the clear and understandable results. Similarly, if you consider another problem, suppose there is a drag force acting on a sphere. Okay, so the parameters which will affect, okay, the force on the sphere, the parameters which will be there, that will be diameter, velocity, rho, that is density, and viscosity. All these will be considered while calculating the drag force. But again, you have to perform number of experiments. Okay, and you have to vary each term, so there will be so many combinations. So to avoid that, you have to again use this technique of dimensional analysis to reduce this again 5 number of variables including dependent variable into only 2 number of variables. So if you say the only 2 number of dimensionless numbers, that is f upon rho v square d square, it is one dimensionless number, and again rho vd by mu is a second dimensionless number. So again you are getting the same graph as of the previous problem. So this technique is very useful. Now let us see how we are going to perform the dimensional analysis, because there is a numerical coming in the exam on dimensional analysis, and to solve that numerical we have to know the procedure for the solution of the problem. So one of the method for dimensional analysis is known as Buckingham pi theorem. In this you are going to use some non-dimensional numbers that these are called as a pi terms or pi pi theorem. Now remember, we have seen the main objective of dimensional analysis is to reduce the number of variables for simplicity, okay, for obtaining the solution, as well as to reduce the number of experimentation. So there is a standard procedure suggested by famous scientist Buckingham. It is based on the idea of dimensional homogeneity. That is, you are equating the two dimensions, and then for an equation the dimensions on both the sides are equal. That is called as the dimensional homogeneity. In this method, the given number of variables are reduced into dimensionless numbers known as pi terms, hence the name Buckingham's pi theorem. This is very interesting method. Let us see the procedure for Buckingham's pi theorem. Now if you see here, we have clearly mentioned the steps involved in the Buckingham's pi theorem. Now there are total 8 steps through which you have to go for obtaining the solution of the given problem using Buckingham's pi theorem. Step 1, you have to list all the variables including dependent as well as independent variables. Let all the variables be n, small n. Now you have to express each variable in terms of basic dimension. Basic dimensions are mass, length and time. That is nothing but m. Generally the number of basic dimensions is equal to 3. Step 3, decide the required number of pi terms. Now the total number of variables are n, and you have to reduce that number of variables into dimensionless numbers that are called as a pi terms. So that pi terms are nothing but n minus m, small n minus m. So if there are 7 number of variables and 3 number of basic dimensions, then your pi terms will be 4 only. So the number of equations are reduced by using this. Step number 4 is select the number of repeating variables. This is very important term. Repeating variables are nothing but they are selected for obtaining the solution of the given problem. So in this you are selecting the repeating variables equal to the number of basic dimensions, and that is generally 3. All the numericals are generally including all 3 basic dimensions, that is mass, length and time. That's why repeating variables are also equal to the dimensionless number basic dimension, that is m, l and t. So it is generally 3. So how to select that repeating variables, that we'll see in the next slide. Before that, step number 5, it is formation of pi terms. Now after selecting the repeating variables, you have to assign the pi term to each of the non-repeating variable using these repeating variables. So we'll see, repeating variables means they will come in each pi term. That's why the name is repeating variable. Step number 6, repeat the step 5 for each of the remaining non-repeating variables, as you are assigning each pi term to each non-repeating variable. So you have to perform the same procedure, that is the homogeneous equation. You have to apply the homogeneity, that is dimensional homogeneity, for each of the equation, that is for each of the pi term, and you have to get some relations between the repeating and non-repeating variables. Okay. So that we'll see while we will solve the numerical. Step number 7, checking of the pi terms. You have to check the given pi terms, okay, the given non-dimensional numbers that you have to obtain. And step number 8 is final form of the relationship among pi terms. Now you have to obtain the given solution by using these pi terms, that is the dimensionless numbers. Now these pi terms are having some properties, that whatever is first of all, these all are dimensionless numbers. They are not having dimension. So it is very easy to play with the pi terms, that you can multiply. If you multiply 2 pi terms with each other, suppose you multiply pi 1 into pi 2, you can take it equal to pi 3. Okay, so 2 pi terms can be replaced by the product, by the division also. Okay, so it is very interesting to solve the numerical based on Buckingham's pi theorem. There we will use the properties of the pi terms. Now let us see the method of selecting the repeating variables. Now I have told you that you have to use some repeating variables among the pi terms. Okay, so the repeating variables, I have told you that there should be the repeating variables equal to number of fundamental dimensions, that is m, l and t. So three fundamental dimensions are there, so repeating variables are mostly three. So how to select these repeating variables? So which variables you can take as a repeating variables? So there is standard procedure defined by Buckingham that while selecting the repeating variables, the first variable should be a geometric property. Geometric property like length, diameter or height. Second variable should be a flow property. Flow property means like velocity of the fluid or acceleration. And the third property should be fluid property like your viscosity, density or specific weight, like this. So all this should be in a proper manner. The selection should be in a proper manner. Geometric property should be selected first, flow property should be selected second, and the fluid property should be selected as a third repeating variable. So this is the selection of the repeating variables. Generally most of the problems include the repeating variables as a d, nu, rho. D is a geometric property, nu is the you can say the flow property, that is sorry, d, v and rho. D is a geometric property, diameter, v is the velocity and rho is the density. So it is by mistake it is written as nu. It should be v, capital V, velocity. Okay. Now let us see the numerical. So from numerical the things will be very clear to you. Friends, the numerical on dimensional analysis are very simple. Once you understand the procedure, how to solve it, they are very simple in the exam. So first, let us read the problem. The pressure difference delta P in a pipe of diameter capital D and length L due to viscous flow depends on the velocity V, viscosity mu and density rho. Using Buckingham's pi theorem, obtain an expression for delta P. Now straightforward we have to obtain the expression for pressure drop delta P using some independent variables. The independent variables in this case are diameter D, length EL, velocity V, viscosity mu and density rho. So in all total, if you see in this numerical, first you have to list out all the number of variables, dependent as well as independent. So if you see, there are delta P, D, L, V, mu and rho. So total 6 number of variables are there. So if you see, the function of delta P, D, L, V, mu and rho, it is equal to 0. So this is just procedure. Likewise you have to write. So total number of variables are 6. Small n is equal to 6. Number of fundamental dimensions, as I have told you, it is generally most of the problems include M, L, T as fundamental dimensions. So you can write the dimensions of each and every term in detail, because dimensions are required for the homogeneity, okay, dimensional homogeneity. So you have to find the dimensions of each term, dimensions in the form of M, L, T, okay, for delta P, D, L, V, mu and rho. So M is equal to 3. So we have seen that number of pi terms will be n minus 3, that is 6 minus 3, so 3. So in this equation, in this problem, there will be 3 pi terms, pi 1, pi 2 and pi 3. So function of pi 1, pi 2, pi 3 is equal to 0. Okay, now this each pi term is assigned to the remaining 3 non-repeating variables. 3 are repeating variables and remaining 3 are non-repeating variables. That's why the pi term, pi 1, pi 2, pi 3, these are written in terms of repeating and non-repeating variable. Okay, so pi 1 is written in terms of repeating and non-repeating. Before that we have to select the repeating variables. So repeating variables, we have seen that first should be the geometric property, second should be flow property and third should be fluid property. So geometric property in this numerical, it is taken as capital D, diameter, flow property as velocity and fluid property as mu, that is viscosity. So the diameter is the geometric property, V is the flow property and mu is the fluid property. So you can select L, that is the length, also as a geometric property. Velocity, there is no R for velocity, so velocity should be there for flow property. And you can have rho as a repeating variable also, because it is also a fluid property. So it depends on you, whatever you are selecting as a geometric, flow and fluid property, no problem. Okay, but the remaining 3 will be then the non-repeating variables. Okay, generally the dependent variable is not selected as a repeating variable or repeating variable. So here dependent variable is delta p, so don't select delta p as a repeating variable. So d, v, mu are the repeating variables which will occur in each of the pi term. So pi 1 will be equal to d raised to a1, v raised to b1, mu raised to c1 into delta p. Pi 2 will be d raised to a2, v raised to b2, mu raised to c2 into L, and pi 3 will be d raised to a3, v raised to b3, and mu raised to c3 multiplied by rho. So if you see pi 1 is a dimensionless number, so its dimension will be m0, l0, t0. D is the length, so it is L raised to a1. V is the velocity, it is meter per second, so it is L t minus 1 raised to b1. Mu is the viscosity, so viscosity, you know, its unit is kilogram per meter second, so its dimensions are m1, L minus 1, t minus 1, so it is raised to c1. And delta p, it is Newton per meter square, so it is again in terms of mlt, it is m1, L minus 1, t minus 2. So if you do the dimensional homogeneity, that is the equating the terms on left hand side and right hand side as for m, L and t. So for m, if you see on the left hand side all the terms are 0. So for right hand side you will add all the indices of m, L and t and equate it to the 0, that is to the left hand side. So if you see, there are 3 equations obtained. When you equate for powers of m, then you will get 0 is equal to, for m to the right side it is c1 plus 1. So c1 plus 1 is equal to 0. Hence you are getting c1 as minus 1. Similarly for power of L, that is the length, you are getting 0 is equal to L raised to a1. So it is a1 plus L raised to b1. So a1 plus b1. L raised to minus 1 raised to c1. So it is L raised to minus c1. And lastly L raised to minus 1. So it is 0 is equal to a1 plus b1 minus c1 minus 1. So you are getting a1 in terms of b1 and c1. So c1 already you know, you put the value of c1 here till you don't know b1. So you take the third equation for time. 0 is equal to minus b1 minus c1 minus 2. So b1 is equal to minus c1 minus 2. So you are getting b1 as minus 1. So when you are solving for b1 or putting the value of b1 and c1, you are getting the value of a1. So you are getting c1 as minus 1, a1 as 1, b1 as 1, that is b1 as minus 1. So you are getting the term pi 1. If you put the values of a1, b1, c1 in the pi terms, you are getting the value of pi 1 as pi 1 is equal to d raised to plus 1, v raised to minus 1, mu raised to minus 1. So you are getting into delta p, you are getting pi 1 is equal to d into delta p upon mu v. So this is the first dimensionless number, that is pi 1. Similarly you perform for pi 2, which is equal to d raised to a2, v raised to b2, mu raised to c2 into L. L is the length. Okay, so again you are equating the powers or the indices of m, L and t on both left hand side and right hand side. So you will get 0 is equal to c2 and 0 is equal to a2 plus b2 minus c2 plus 1, and 0 is equal to minus b2 minus c2. So if you solve these equations, you will get c2 0, a2 as minus 1 and b2 as equal to c2, that is equal to 0. So when you solve for pi 2, then you will get pi 2 is equal to d raised to minus 1, v raised to 0, mu raised to 0 into L. So you are getting simply L by d. Similarly for third pi term, you are getting pi 3 is equal to d raised to a3, v raised to b3, mu raised to c3 into rho. So when you solve for the third term, that is pi 3, again equating m0, l0, t0 to the right hand side, L raised to a3, lt minus 1 raised to b3, ml minus 1, t minus 1 raised to c3 into rho. Rho is ml raised to minus m1 l raised to minus 3. So when you solve for m, l and t again, as per the previous two pi terms, you will get the value of c3 as minus 1, a3 as plus 1 and b3 as plus 1. So you put the values of a3, b3 and C3, you will get pi 3 is equal to d raised to 1, v raised to 1, mu raised to minus 1 into rho. So you will get simply rho vd by mu, and pi 3 is nothing but Reynolds number. We know rho vd by mu is Reynolds number. So again you are putting the values of pi 1, pi 2, pi 3 in the equation. F1 is F1 as a function of pi 1, pi 2, pi 3, which is equal to 0. So you can write f pi 1, pi 2, pi 3 is equal to 0. So pi 1 value, pi 2 value and pi 3 value you have to put in that equation. And I have told you that there are some properties of these pi terms. You can have the combination of, you can take the pi term out of the bracket and you can write one pi term as a function of other pi terms. So here pi 1 can be written as a function of remaining two pi terms. So if you write d rho delta p upon mu into v, that will be equal to function of L by d rho vd by mu. Rho vd by mu is a Reynolds number. So delta p is a function of mu into v upon d into delta p is equal to mu into v upon d into function of L by d into Reynolds number. And simply you are getting the final answer as delta p is equal to mu v by d into L by d, because L by d is again a you can say it is a linear, it is varying linearly with delta p. That's why you can take it out of the function and you can take it is a only function of Reynolds number. So in short, delta p, you know, that is hf is equal to delta p by rho g. So you can write hf is equal to delta p by rho g, which is equal to mu v by d into L by d into 1 by rho g into function of Reynolds. In short, hf is a function of Reynolds number. And the last term, that is the model analysis. The model analysis, it is a simple scientific method to perform the hydraulic structure systems and machines. When you there are two terms. One is called as a model and one is called as a prototype. So when you are performing the experiments in a laboratory, that is called as a model, and when you are when you are going on the actual structure, that is called as a prototype. So when you want prototype, so before building the prototype, you are just building a model first in the laboratory. So for building the model, you should correlate between the model and prototype. How you are going to correlate? So for that you are using some model analysis, that is called as a hydraulic similarity. So you are equating some properties on the model to that of the prototype. So when you are equating the geometric properties, it is called as a geometric similarity. When you are equating some kinematic values like properties like velocity, acceleration, then it is called as a kinematic similarity. And when you are equating the forces, okay, on model and prototype, or equating means you are taking the proportion of these forces, then it is called as a dynamic similarity. So three types of similarity include are there in this model analysis. First one is geometric similarity. In this, the prototype and model which are identical in shape but are different in dimensions or size. So the ratio of corresponding linear dimensions are equal. Okay, so the dimension of the length on model and the dimension of length on prototype, the ratio of them, that is equal to the diameter of the model and to the diameter of the prototype. So the geometrical relationship. Similarly, the velocity of the corresponding point on the model will be equal to having the or you can say the same variation on that of the prototype. So if you take the ratio of the velocity on that of the model to the prototype, then that ratio will be at one point will be same as that of the 2 points. Okay, so that is called as a kinematic similarity. And the forces, now we know there are different types of forces: inertia force, which is inertia force, or you can say shear force or viscous force. The ratio of inertia force and viscous force is called as a Reynolds number. So in short, dynamic similarity gives you the equating the dimensionless numbers like Reynolds number, Froude number. All these numbers are giving you the dynamic similarity. So in short, model analysis includes the similarity between the model and prototype. Okay, but the main focus in this dimensional analysis is on Buckingham's pi theorem, because there is one numerical coming 100% in the exam on Buckingham's pi theorem, and you have to solve that numerical. So you have to make practice of the numericals on Buckingham's pi theorem, and you have to solve that numerical. No need of solving the numericals on model analysis. It's the only theory part we have covered here, but the numerical mostly it is coming on Buckingham's pi theorem. So you have to practice for the numerical on Buckingham's pi theorem. I hope you have understood the Buckingham's pi theorem. Solve for more number of numericals. With this, the unit number 5, that is flow through pipes, is completed. I hope that you will solve all the numericals related to all the 3 sections of this unit. So best of luck. Thank you very much.